Log on, tune in, find out. Another good idea from Cambridge.
He's also worked outside academia. He's been an expert in many legal cases, obviously involving statistics. And he worked for Renaissance Technologies in the US in 2005-06. Now, I'm not exactly sure of the timing, whether it was that year or the year after, but I know that Jim Simons, I believe, made $1,500 million. He's the guy that year. He's the guy that runs Renaissance Technologies. So I put it all down to David, and we're incredibly fortunate to have him on a Cambridge professorial salary. Over to you, and thank you very much. I should explain, there is a tradition. This is an hourglass, but for a guy as experienced as you, I suspect I won't need it. There have been previous visiting professors who said, well, all I'll do is just turn it over at the end.
Can everyone hear me? Okay, thanks for the nice introduction. However, I think this method of profit attribution is a bit faulty because I also worked in oil exploration for a couple years. In fact, my only previous lengthy stay in England was working for Aramco, the Saudi oil company, on oil exploration. And I sure wish I could attribute some of the profits that are being achieved by Aramco to my stay, but I doubt that that's true. I want to talk about what's initially going to be extremely very elementary, because I don't know the common background that people have, essentially setting up some common prejudices that everyone has drunk in about systems of linear equations from their university and even earlier courses where they would have learned some algebra. And then I'll talk about experiments which are being done by applied mathematicians, people in signal processing, image processing, and people in medical imaging and so on, that show there's something wrong with the intuition that's been fostered by all of those early experiences in algebra. And after I've given you some practical evidence about the defaults that we're creating through our instruction, we'll tell you a bit of deeper math that says that it's not, let's put it this way, that there are some very interesting phenomena. It's not that algebra is wrong, but that we've left out a part of the picture, and there's a lot of interesting pure math that needs to be done to match up with the applied math that is being done. Okay, so let's start very, very simply. I was here for the Science Week lecture that was held on Saturday. That was designed for an audience of 14 plus. So I may be starting at too low of a level, but from some experience I found that it never really hurts to make sure we're all on base. Okay, so two equations and two unknowns. You might have seen this in, I don't know, 8th grade. And we know that this system has one and only one solution. The understanding of the phenomena that are underlying such systems is a prerequisite for being considered a relatively smart person in lots of lines of work. And the basic reason that two equations in two unknowns might have a unique solution is indicated from this, again, probably from a college algebra or earlier textbook. I got this off of Wikipedia. The first equation that we had, x minus y is minus 1. The second equation, 3x plus y equals 9. And since 10th grade or earlier, you probably know that in the Euclidean plane, lines intersect in a point or else they're parallel. The generic situation is they intersect in a point. Two equations have a unique solution, the point of intersection. Okay. And we understand from that geometric picture that while we could consider a variety of situations where you have different numbers of equations in two unknowns, there are only sort of three things that could happen. The first one is we have one equation, in which case there is no unique solution because it's not enough to determine our position. We could have two equations in general position, and then we get a unique solution. We could have more than two in general position, and then there's no solution. Any pair of those might have a solution, but it would be a miracle if they have a common solution. Okay, so this is quite understandable, and is the content of various school mathematics courses. We move on, we can have 3 equations and 3 unknowns, and in fact, the particular system that's written here has one and only one solution. The reason for that is that 3 unknowns, the state space can be viewed as Euclidean 3-dimensional space, and an equation of the kind that we had on the previous slide specifies a plane in the 3-dimensional space, and the generic situation is that 3 planes will intersect in a point, and that point of common intersection is the unique solution of those equations. Actually, I also got this off of Wikipedia, which had a very cool link to explain this, which I learned something about teaching from this. Secret sharing. So if you and 2 other friends have a secret that you want to share in such a way that the knowledge of this secret is not available to any one of you alone, but only to the group of the 3 of you separately, for example, the location of a buried treasure, then what you should do is pick some set of equations in general position that has that particular solution as that specific point where the treasure is buried, and let each one be the guardian of the set of equations. And then when you come together and intersect your planes, you know exactly where to go dig. So let's just hope that it doesn't end up in some kind of acrimony like in the treasure of Sierra Madre. In any event, if one of your friends out of the 3 of you who are in cahoots on this treasure for some reason passes away or disappears, then you're in a difficult situation, because as you can see, all that you would know is that the treasure is somewhere here along the line. And so if we have only 2 equations but 3 unknowns, you're in trouble. And of course, this is a sign of a general phenomenon. If we formalize things using a standard notation, we could actually have n equations and p unknowns denoted as a system of equations like so. And we know in general that if n is less than p, there's no unique solution. Instead, there will always be infinitely many solutions. If n is equal to p, then generically there'll be a solution that's unique. And if n's bigger than p, there's generically none. Now, this basic fact is so important for being an educated person that it's used throughout science and technology, and I dare say finance and other fields. Scientists and engineers generally call this parameter counting, because the number p of parameters of the solution has to be equal to the number n of measurements or observations that you make. And so that's sort of the first sanity check that's ever done by a scientist on looking at if a set of information is enough to determine what you need is to do parameter counting and see if you're in a successful region for a solution. Okay, are there any questions so far? Am I insulting people? Okay, well, okay, this previous notion of setting up systems of equations can be a little more compactly represented with matrices and vectors. So we can write out that the table of coefficients A as an n by p array. We can have x be a p times 1 vector, y an n times 1 vector, and the meaning of the system of equations is we know the left-hand side and we know the coefficients in A. We want to recover x. So we know that this problem is underdetermined if there are fewer rows than columns of the matrix A. And that, again, a sign of intelligence to understand that this is the case. On the other hand, recently, over the last decade or so, I think it's also understood that where a great deal of money and human welfare is at stake, no one is going to stop and listen to a bunch of mathematicians tell them that it's impossible. In particular, we can find lots of cases that are out there where there are tremendous numbers of people spending a lot of money and effort on problems that have exactly the form of underdetermined systems of equations. So if we're in digital communication setting, it would be generically the case that there's a relatively small number of fixed antennas, say associated with standard CDMA wireless, the kind of things that you might have in connection with cell phones, or I think they're called mobile phones over here. So a fixed number of antennas and many, many transmitters walking around in people's pockets and so on. In remote sensing, we might get a limited number of samples, but be essentially trying to make measurements about a continuous field quantity, such as the Earth's magnetic field or the exterior field generated by the electromagnetic activity of the heart, something like that. So there's in principle an infinite number of unknowns, but a finite number of samples. And in genomics, we might be interested in enrolling a small number of patients in a study and then measuring gene activity. And those patients, maybe some of them would be afflicted with some dire symptoms, and we're trying to find out which genes are the ones that are related to that. So this is happening actually in a lot of fields, and even though they have n less than p, you don't see the world grinding to a halt. In fact, it could possibly be true that throughout science and technology, you have people who are blithely going their own way and ignoring the fact that systems are underdetermined. Let me just make these examples a little more real, again, because I don't know our common language and background. In genomics, a situation could be approximately described like this. Excuse me, the people who are real experts at this, if I distort your field. I hope that it's not an horrible distortion, but I'm trying to communicate a basic idea. Let's imagine that we have an outcome variable that is measuring the strength of a patient's symptoms, which might be no strength up to high strength. And we go in and measure gene expression levels for a patient, and at the same time there's an unknown extent to which a gene contributes to a symptom score. A gene may not be at all involved in the outcome. I put in a wiggle rather than an equality. This is really a problem in statistics, and I'm not going to talk too much about noise, even though the Newton Institute program is about statisticians, just to say that this is a simplification of what we do, and I can't get into everything, so I took a simplification. Now, what happens in this case is that we have a relatively small number of patients and a relatively large number of genes. In fact, it's kind of amazing that there's only 30,000 genes. You would naively think that in all those terabases that are sitting out there that there would be many more. But anyway, that's what we're told. Now, why are there so few patients in one of these studies? The reason is that you might not get patient compliance, or you might not get patients who have exactly the admission characteristics that you need. So you have to, in some cases, work very hard to enroll patients, and in many cases there's a very serious cost of even having one patient in the study. So we could talk about individual diseases and syndromes to illustrate that, but perhaps the point is clear. The skeptic could just say that medical costs are inflating too rapidly, but I'll leave that aside. Here's in another field, error correction. Imagine that we receive a bit, and the bit is equal to transmitted bit plus whatever error happened in the transmission. We could think of this as a system where y equals ax, with x being the vector of transmitted bits and errors, and the A matrix looking like having some ones in certain positions, 2 ones in every row. There would be a total of n rows and 2 n columns. And essentially then we have a situation with n observations and 2n unknowns. So the problem of determining what errors have been made in a transmission, at least at this level of generality, is an example of an underdetermined system. In signal and image processing, which is a place that we'll spend a lot of time early on in the talk, there are, I think, many interesting examples that one could come up with, and these have a connection to the Sir Isaac Newton, which I'll try to get to as we go through the talk. Simple example is you're at a cocktail party and there are many people speaking all at once, and you have a limited number of microphones. So just as we are at the moment in this lecture hall, there are order of magnitude 80, 100 people here. There's order of magnitude, I don't know, 10 microphones. And so if we have less than one microphone per potential speaker. And if we were, if we broke out the beer and all started talking, then we would have the problem of, let's say, out of all of those different microphones up there, demixing all the sound so that we could pull out Sir David's voice or one of your own particular voices from this conversation would be an example of an underdetermined system. In that case, N would be the number of microphones, and P would be the number of potential speakers here present in the room. If we had many instruments playing music all at once and we wanted to separate out, we could have a similar problem. So there's these component separation problems. In astronomy, people who do extragalactic astronomy and look at the formation of galaxies at the far, far reaches of the universe are interested in the fact that gravitational instability causes an initially scattered, quasi-random distribution of matter in places to compress into filaments, in other places into sheets. Sometimes the sheets and filaments and even point-like structures overlap. So there are distinct geometrical types. They would like to be able to separate all of that out in some sense. So that's separating out into 3 layers. But there's sort of a certain number of voxels in such imagery, and each one of these has the potential of occupancy per voxel. So you get, if they're p pixels, then you have something like 3p unknowns. So in any event, you can see that these things come up a lot in imagery, and we'll get more examples of that. To have a little bit of math and kind of get used to some of the things that can happen, let's make a caricature of one of those separation type problems. It might provoke some discussion. Suppose we observe a signal y at locations 1 through n, and that signal is a superposition of 2 sorts of things. First of all, there's some sinusoidal component, and secondly, there's a spike component. In this particular case, there's 1 sinusoid and 1 spike. Okay? Now, if we don't know the frequency of oscillation of the sinusoid and we don't know the location of the spike, then in the way that I've digitized the problem, then the sinusoid could be anywhere between 1 and n, and the spike could be anywhere between 1 and n. And so we could set up a matrix that has n by 2n aspect ratio, and in the first n by n submatrix would be these sinusoid terms, and in the second half would be essentially the identity matrix. Okay, so there are many underdetermined problems, and we'll come back and see more of them. Now, I want to talk about the role of sparsity in solving these problems. Many of you may have heard of sparsity in connection with systems of equations, and that would be a different sense of sparsity than what I mean here. There are sparse matrix packages, sparse linear algebra. What usually is meant there is that the matrix A has very few non-zeros. It's going to turn out to be here that you actually like the matrix A to have many, many non-zeros, not very few. But what you're hoping is that the right-hand side that you're solving for has relatively few non-zeros or relatively few big elements. Maybe they're not, maybe there's some, maybe there could be many very small numbers, but only a few big numbers that matter. Okay. Sparsity is describing settings where most of the variables in the solution that you're seeking in this underdetermined set are inactive, but we don't know a priori which ones those are. So there's this possibility that the spike could be anywhere, and there's this possibility that the sinusoid could have any frequency. We're not going to say a priori what it is. And we see sparsity all the time without necessarily remarking on it. In digital comm, essentially the key point is that there's going to be few transmitters at any one time. So that there's this fixed system of antennas, and the people who run the mobile providers like Orange and others have figured out how many of those antennas have to be put out there to deal with the typical loads that they see. But they're quite comfortable with the fact that not everybody is going to make a mobile phone call at the same time. Similarly, we have this array of microphones, and I guess it's based on the principle there are going to be less than about 8 speakers at any moment. And maybe even one is typical. So sparsity is often the rule in this hall. In genomics, maybe the idea would be that of the 30,000 genes that are active, what you hope is that one or at most a few are going to be responsible for whatever syndrome. If the syndrome is something that involves interactions between many, many genes, it's thought to be extremely difficult for current technology to find. Okay, any questions? So what we're going to talk about now is methods for finding solutions to underdetermined systems that cope with the indeterminacy by looking for situations where there's relatively few active variables, so that most of the entries in X are going to turn out to be 0. And there's a lot of intellectual benefits, as we'll see. You get some very fun math from looking at this, but also there's practical benefits. Now, this is not a topic that has a long literature to it, although off and on in all sorts of scientific and technology fields, people have wanted to do this. But there's a basic looming problem, which is that if we just write it out like that, we would believe that what we have to do to find a sparse solution is basically enumerate subsystems of our system until we find one that has the proper format to be exactly determined and is exactly determined, and we would go through and do everything to enumerate the potential solutions. That's a classic combinatorial optimization problem, and many NP-hard problems can actually be written as finding solutions exactly with very special kinds of matrices A. So there's sort of knapsack problems and satisfiability problems that are well understood. So it doesn't seem practically promising to pursue this if you read the theoretical CS literature, but because of some math coming out of convex analysis, you'll see that the situation is a little bit better than that. I thought to organize the talk today by first of all talking about practical results that some former students and postdocs and so on of mine have gotten, and then talk a bit about some math that explains why those practical results are possible, and maybe even more is possible. And then I'll talk about some of the activity that's going on in the field. In about the last 3 or 4 years, many papers have been published relevant to what I'm talking about today, so much so that I can't even list all the authors, although I'll try to give you a list towards the end. Okay, this is Isaac Newton's own hand, and it's supposed to be from his notebook. And what you are seeing here is a sketch where he's determining that the prism is really separating things out into monochromatic light. So here's the first prism, and then there's a barrier here, and there are pinholes. Light goes through the pinhole to a second prism, and there's no further demixing going on. So Newton, either he invented the prism or he was the person to recognize the extremely important fact that prisms are performing a separation of a kind of mixed content into a pure content. And he did the scientific experiment to prove that. Now, it took hundreds of years for a full, say, mathematical understanding of this. This is an analog device. The mathematical counterpart of this is now called Fourier analysis. And we use fast Fourier transform every time we download web pages. In effect, the transform is applying Newton's prism to the scene, and it's doing a kind of spatial separation rather than a separation in color. But there's a complete and perfect isomorphism between what was going on there and what's being done by your web browser every time it looks at JPEG. Okay. In any event, this has been a fantastic conceptual advance in science, and it's very little remarked on when the popular mind thinks about Newton, and commentators and so on go into some of the big contributions. But it's dominated my life, and I think my life is important enough that I can bring this up here as a fundamental contribution. Only it's important to me. I'm not claiming more than that. However, there's something beyond what Newton did and the follow-on work by Fourier and others. There was this notion of color, and color is essentially a cognate for the frequency of a sinusoid. And what Newton was effectively doing is breaking up something into a superposition of sinusoids. All those examples of that turns out to be a well-determined system in the way that it's traditionally written down in mathematics, so that we could write a square matrix with as many rows and columns and do a Fourier transform, and we're essentially solving a well-determined problem, not an underdetermined one. However, the needs of science and technology want some sort of generalization of the notion of color, where we're not just breaking stuff up into frequencies, but we're breaking stuff up into a more general set of entities, one of which may well be a Fourier analysis, and another might be another system. So the Mathematics Awareness Week poster for 1998 was developed by Rafi Koifman and Francois Meyer, and they there showed taking this classic mandrel and separating it out into completely different systems that involve the texture and the geometry, they said, of this underlying picture. Now, the texture was a kind of local Fourier analysis, so we apply Newton's prism to little blocks of the image in a certain sense. And the geometry was some kind of wavelet analysis. So another tool was being used. But the idea was more than one representing system. And if we try to model this as systems of equations, then we'll see that it's something like n by 2n. So it's an underdetermined system, and you could argue this doesn't make sense. How can we be doing this? So Scott Chen, in his Stanford thesis, looked at a particular problem of this kind, and here's an example where he took a sum of just two sinusoids and two spikes, where the frequencies could be anything in the standard list of Fourier frequencies, and the spikes could be anything between 0 and n-1, and tried to develop a representation of that using a principle which we'll talk about in a minute. This principle called basis pursuit, which I'll talk about, separated out this signal, which contains the sinusoids and then two spikes, into sort of a thing that goes beyond a spectrum, or what Newton's prism was breaking things up into, two panels. One of these, discrete cosine transform, was a color decomposition, and the other one, looking for spikes, was a representation in terms of spatially highly localized things that would be themselves composed of all possible colors. So a decomposition was found in terms of a very simple combination of four terms, which in fact was the exact thing that had made up this signal. And it goes beyond classical Fourier analysis or Newton's prism, because two systems of representation are involved. It's an underdetermined system. Now, when you're dealing with underdetermined systems, you could imagine that maybe you're lucky in one particular case, and you just happen to be right. But he did lots of experiments, varying conditions, and it turned out that even if you shrunk down the spikes so that you couldn't even see them, but they were still there, you still got them correctly with this thing. And at any dynamic range, you'd still get them. On the other hand, an algorithm called matching pursuit, which was developed by Stéphane Millat and Yifeng Zhang, didn't work so well. And that's what would happen if you just were heuristic and didn't have theorems to help you out. So you can see that the true frequencies are indicated by these bars, but some heuristic algorithm is not able to find, the actual decomposition. So what did he use? The idea was that you have a collection of matrices, each one of which could be used as a well-determined system of equations, but you glue them together, creating a matrix that's not square, that's wider than it is tall, and you minimize the L1 norm subject to the data you have, which is some observed signal, and try to find coefficients. And that's what was being presented, and which correctly gave the decomposition. So together with Michael Saunders, who works in optimization, we published a paper in Siam Journal of Scientific Computing, which was later reprinted in Siam Review. Xiaoming Huo, who's now a professor at Georgia Tech, did the following experiment, which was, let's consider representations that go beyond, I think, maybe what Fourier had imagined, and we'll have a system of wavelets and a system of curvelets. Curvelets involve parabolic scaling. They're multi-scale representation with directionality, and this again makes an underdetermined thing. We could represent an image with either wavelets or curvelets. When we put in both, it's underdetermined, and what we get is this decomposition. The side images are just the original. And what you see is that the curvelet part gets the geometry, and the wavelets get the jaggies and the very coarse scale stuff in the blush of the cheeks. So some sort of representation has been found that separates out the content types. Jean-Luc Stark, who's now at CEA Saclay, was a postdoc with me and later visiting scientist, and he did a decomposition of galactic imagery that by using two different systems that each by themselves gave a complete image representation, looking for the L1 minimization, was able to separate out the gas from the point-like object. And he continued and used multiple systems to separate out for certain kinds of instrumental imagery particular decompositions where he could use, say, 3 different systems and pull them out. Michael Elad, who's now a professor at the Technion in the computer science department, worked with Jean-Luc in 2003, and they made a decomposition of Barbara into 2 pieces. Now, over here, I think, is the original Barbara that you may have seen if you attended any image processing talks in your life. But this is not the original Barbara. This is Barbara that doesn't have striped pants, that doesn't have a striped scarf, whose tablecloth is not a checkerboard. That's because there was a decomposition was made into 2 systems. One, using curvelets, will capture geometry, things that have curvilinear boundaries, and the other one, using local Fourier analysis, will capture the texture. And again, even though this seems like an underdetermined problem, that was not a that conceptual thing was not a hindrance to carrying out these experiments and getting a result. Spectral super resolution is another thing of practical interest. Suppose that what you observe is, well, this is just like Newton's problem. You observe a superposition of sinusoids with non-negative coefficients. How many measurements do you actually need to resolve that? So the orthodox idea would be that if the frequencies range through a grid like this, then we need p measurements. And why? Well, because then you get a determined system. It's just determined. That seems right. Okay? But what if it turns out that your light source, or whatever the source of your signal is a superposition of a small number of monochromatic things, or essentially monochromatic things? So then it would be sparse, and that would be something that you could exploit. So, well, here's the first instance of a theorem, and I guess in this terms you can see it. Jared Tanner, who's here, and I have a paper in PNAS that pretty much states it this way. But it goes back earlier, and you could even see hints of it in Cara Teodori in 1907. At least the underlying reason that it's true was a phenomenon known to Cara Teodori. Anyway, if you define a matrix as done there and say, well, this is what I observe, I don't know these x's, find the minimum L1 norm of any x that has this, and I guess I left out x greater or equal to 0, then provided I had at least 2k plus 1 samples and there's no more than k non-zeros, I get it back. So I don't need to measure n things. I need to make 2k plus 1 measurements. Okay, here's an example. George Zweig, who at the time was a scientist at Sandia Labs or Los Alamos, I forget which. This is plutonium EXAFS. It's a kind of spectroscopy. And this is still, again, the problem of Newton's prism, but it turns out to take the digital realization of Newton's prism is very costly per observation. And with the data that they got, using classical numerical Fourier analysis, this is what they would have seen. But applying the method of minimum L1 reconstruction subject to positivity, this is the resolution that was obtained. Okay? Now, the point is that you can outdo sparsity allows you to outdo what linear algebra would ordinarily prescribe. Okay, so once it sort of frees your mind that you can do things with fewer equations than unknowns, you start being pretty daring. And one thing you could do is look at all sorts of scientific measurement problems and propose that perhaps they could be reformulated and not so much data needs to be gathered. So in this setting, if we can somehow transform a problem that's out there where people are making a large number of measurements into a setting where there's some sparsity of the object that we're interested in, then maybe we don't need to make all of those measurements. And so this is just sketching out some of the formalism. Basically, if the object in question F could be some image, can be represented as a sparse linear combination of some basis functions. And if we take something that's kind of a random matrix for our measurements and define A to be the composition of the basis matrix and this random sensing matrix, then the same prescription we're talking about would allow us to reconstruct the object. Emmanuel Condez, Justin Romberg, and Terry Tao gave an example of this kind in tomography in 2004, and then about the same time I wrote a paper called Compressed Sensing that sort of formalizes this in a general setting. Since then there have been many papers, and just to give you an example, Yaki Tsaig was my grad student, and we did just a numerical applications paper on this. I just learned that it was the most cited paper in the journal Signal Processing in 2006. We just showed that you could do it, and here were some of the examples. Here's a blocky object, and it nominally has 2,000 unknowns, but we only made 340 measurements, and provided now somewhere below that, around 256, one doesn't get a good reconstruction, but with 340 you get a great reconstruction of the object. Or here's a simple object that has a sparse representation in a kind of Haar wavelet basis, and you can see that you don't need anything like the nominal number of measurements. It would seem that you need 1 million measurements to get this, but in fact 1152 gave us the reconstruction in the center, which has quite a good approximation error if you go into the measurement details of it. And you can do model problems of tomography and so on. Michael Lustig, who just got his thesis at Stanford and works in the MRI lab, a very bright young man, has in 2004 heard, we had been working together since 2002, and he heard about the possibility of doing these things, immediately ran to the MRI scanner and implemented it. And if traditionally, if you just did some kind of undersampling, it's called, don't gather as much data as people ordinarily do in MRI, the reason people didn't like that is you get horrible artifacts. But if you do with a minimum L1, as I've said, using the wavelet basis as the generating basis, the artifacts are largely suppressed. And so undersampling doesn't have to face the problems people had seen. So since then, compressed sensing has really taken off in MRI. At the moment, there's, I would say, about 50 papers with the title Compressed Sensing in the upcoming meeting of the Magnetic Resonance in Medicine Society. And one reason that it got accepted so rapidly is there are many physicists who work in that field, and they want the medical people to understand that they can make a contribution. And a big part of making compressed sensing work is that you should design a kind of quasi-random matrix for making your measurements. And so the physicists are having a lot of fun designing very special kinds of MRI scans that are nothing like the plotting scans that you may be used to. So instead of you sit in a scanner for an hour and it goes basically voxel by voxel, making one measurement after another, building up 1,000,000 measurements to give you 1,000 by 1,000 image, they make many, many fewer measurements, but of a much more exotic kind. So Michael Lustig, Juan Santos, John Pauly, and I have a paper in Magnetic Resonance in Medicine, which has actually appeared already, and I wanted to just, if I can find it, show you the movie of the, there's sort of two movies here. If I can find. So this is an 8-to-1 speed up of MRI, and it's in a particular setting where without it, things would be, well, it starts out with a 4-to-1 and then builds up. This is first a model study. If you did traditional linear reconstruction, you get that. That's the true object, and this is what you get with compressed sensing. So using L1. Now, if instead you did on real imagery, that would be trying to cope with linear reconstruction, and that would be with this L1 minimization. So it has fewer artifacts and is just much more valuable use of the data that's out there. I'm going to try to open one more, which is it's useful in imaging the arteries in, well, in this case it's in legs, I believe. So this is a contrast imaging. And what you see, maybe not so well actually, on my screen it's much better. The center is, so these are all based on the same data. This is the exact correct answer. If you used a scan 8 times as long, this is what you get with compressed sensing. If you did some like generalized matrix inverse or linear reconstruction, this is what you get on the side. It's very milky and has a kind of blobby appearance, and nothing like the resolution that you can actually see in this one. However, the contrast is not so good. I'd be happy to show you these on my screen if you'd like to come after the talk. So let's talk about a little bit of math. So we could formalize a problem like this, which is pretty abstract sounding, but many other problems can be coerced into it. Suppose that we have an object. I apologize for the change in terminology. Capital N is the new P. We have an object in high dimensions that doesn't have too many non-zeros, and we measure with a random matrix that's n by capital N. And by random matrix, let's say Gaussian IID entries to have a simple model. And then we solve this L1 minimization problem. So it turns out that there's a phenomenon of phase transition that Jared Tanner, who's at Edinburgh, and I have investigated, and there's phenomena like this, that depending on the shape of the matrix only, there's a threshold that involves how many non-zeros to how many observations. If you're not beyond that threshold, you exactly reconstruct. So Jared did experiments like this. Here's the theoretical prediction we have, and you can see that above this curve you get failure, but below the curve you do well. The color here is a measure of error, and there's just no error below a certain point. And we've analyzed the asymptotics of this. So we get a kind of sampling theorem that says these kind of random measurements of a k-sparse object, then there's a threshold phenomenon that right at this point is where things break. So it is a kind of sampling theorem for objects with sparsity, so it could be distinguished from the Shannon theorem. The Shannon theorem would say that you need capital N, or what I used to call P earlier in the talk, measurements, but that's sort of not part of the problem. And what's the math behind this? I'll just quickly mention two little snippets of math in the 3 minutes I have left. First one comes out of polytope theory, and the second one comes out of the geometry of Banach spaces. Polytope theory, there's something called the Borowski-Henk model, which is we take an object called the standard cross polytope up in high dimensions, and then we take a random orthogonal projection, lowering the dimension from the high dimension down to a lower dimension, little n. And this cross polytope has an image under this dimensional lowering, which we'll call the Borowski-Henk polytope. Okay. Now, what the cross polytope is you take a cross. Okay, in 3 dimensions there would be, front, back, side, up, and you take the unit vector basis and the sign reflections of that. You take the convex hull, and in 3 dimensions you get the octahedron. In higher dimensions you get more. It's like, but it's often called the octahedron even in higher dimensions. But the official name is cross polytope. When you project down, you get phenomena like this. If you project, let's see if I can show you. Okay, here's a projection of a 4D cross polytope down into R3. And it's a centrosymmetric object. And what you see is some vertices land inside. And then there are some vertices that stay. So these were vertices to begin with. And then you're seeing where they land under this projection. So you lose some points in the sense that the convex hull of the object that you form in this lower dimensional space is not going to have those points in it. The concept of losing points is as you lower dimension. Losing vertices, losing edges, losing faces. Okay? And this matches our intuition, which is that somehow, you're going to try to go someplace from one vertex to another, but it's going to hit the interior when you lower the dimension. If you were back up in the high dimension, it would still be an edge, but it's not going to be an edge after you lower the dimension. Okay? So the amazing phenomenon is that if you look at in high dimensional space, this is completely false. That everything that you figured out about low dimensional space is utterly misleading. If you ask how many k-dimensional faces does the Borowski-Henk polytope have, if you look at proportional dimension lowering, so you lower by a factor 10 or something like that, then what you'll see is that there's a threshold phenomenon in such a way that if we look at the ratio, how much the dimension was lowered, and we look at the ratio, this should be k over little n, sorry. If you look at the ratio of the dimension of the face to the dimension you land in under lowering, then there's almost no loss of faces up to some threshold, and then you lose lots of faces above a threshold. So you don't lose vertices, you don't lose edges, you don't lose two-dimensional faces, nothing's lost, up to, boom, you start losing at some dimension. Okay? That place where you start losing is exactly where L1 reconstruction starts failing to correctly solve this underdetermined system. Okay, here's a second piece. So you can read about this in papers that Jared Tanner and I have written, and I'll mention some other stuff at the end. Now I'll just take 1 minute. There's another phenomenon that is very relevant here and uses some quite advanced math, but because of time, I'm only going to give you just a flavor of. And that's the following. You may have thought, well, he keeps mentioning sparsity, and in his locution or construction, sparsity means you have k non-zeros and then a bunch of exact zeros. But that surely cannot be the case in nature. That isn't the way nature is. You maybe have k big guys and a whole bunch of kind of puny guys. These results play out as follows when you start defining sparsity in that more inclusive way. The L1 ball has something to do with sparsity in the sense that if we look at the typical member of the L1 ball, it has a few big guys and a lot of small guys. There's some sense in which the L1 norm is a way to measure sparsity, and even more so, the LP norms with p less than 1, which is the opposite of our school mathematics teaching, measure sparsity even better. So there's this whole family of LP balls with p small. L0 is the case of the sparsity we started with. So it turns out there's a whole scale of results between sparsity with L0, namely a few non-zeros and everything else exactly 0, to sparsity with L1, which is a weaker notion of sparsity. Now, there's this phenomenon that I want to illustrate just with this little emblem. I don't have enough time to explain. It's been known since the 70s that if you look at the L1 ball and you take a random codimension, let's see how to set this up. I'm going to take a codimension n slice through this. And so I'm in capital n-dimensional space. I've got a codimension n slice. Then, depending on the ratio between little n and capital N, I can have this happening, which is that the slice of the L1 ball, this random slice, looks like a sphere. Okay? Now, if you look at the sphere that circumscribes the L1 ball, that also looks like a sphere. But there's a giant difference in the radii of those two things. The difference is some power of n. Like it's like ratios like n to the 1/2 between the guy that you're getting through this slice of the L1 ball and this outer guy. And what that means is that codimension little n slice you can almost think of it as a point. It's very small because its radius is so small. So if your sparse sequence is a typical guy in here and you make enough measurements so that you've localized things down to codimension n, then what you've learned is that you're in a pretty small set. So although you don't have unique reconstruction, you have very accurate reconstruction. And that explains why, again, taking a random matrix of the kind that Jared and I were looking at even works when you don't have the exact sparsity model I first mentioned. Now, in this particular case, a dual result that implies what I just spoke about was developed by Boris Kashin in the mid-1970s in solving the problem of Kolmogorov n-widths of Sobolev spaces. And by applying that through a duality, you can get you can see the geometry. Now again, the low-dimensional intuition is completely wrong, right? Because you feel that slicing this thing gives you a set that's almost as big as the sphere that circumscribes. But it's just not the case in high dimensions. They diverge very, very radically. Okay, so there's math which I'm happy to talk to you about, and there's plenty of papers out there. I'll just mention a number of the people who are working in this field, besides those that are my direct collaborators, for example, Manuel Condez is at Caltech, Terry Tao is at UCLA, and I've mentioned a number of other workers who've done quite interesting things. I suppose I should update institutions. I think Joel Trop is now at Caltech, for example. And many people are doing kind of related things, like a lot of people are coming forward with their own constructions and approaches to do stuff like this. And I really can't summarize it all in an hour. So anyway, what's my point? We started with underdetermined systems. We talked about a prejudice that's been inculcated by school mathematics. And the prejudice is very useful, as has led to a lot of scientific progress. But you know, if you're the NIH and you have $10 billion to throw around for genomics, and a mathematician comes to you and says, well, you've got underdetermined systems of equations, guess what? You're going to spend the $10 billion anyway. And what's going to happen is a bunch of people are going to step forward and tell you how to do it by using some more clever assumptions than what you had learned about in college. And that's kind of what we're talking about here. With more cleverness, bringing more assumptions to bear, in this case sparsity, you find out that things that seem to be obviously impossible are not really. And there are applications throughout science, technology, and even in finance. Thank you for your attention.
Talk, and thank you very much. So we have time for questions or comments. Open up, please.
In the formula you quoted about 5 or 6 slides back from the end, you had n being greater than twice log k upon n times k as the minimum number of measurements you have to take in compressed sexting. Can you say anything about the log k upon n term there and what it really means? Is it, for example, something to do with the information needed to specify the sparse data set?
Well, indeed. Jared and I worked on that project using a bunch of formulas that come out of high-dimensional convex geometry. And there's all sorts of asymptotics of Gaussian integrals and large deviations calculations that we were doing. So the answer from our point of view is, you know, it's just what is. But I know that there are related ways of posing the problem where people have been able to derive the same answer by information theoretic methods. What I mean by the same answer is in our problem, we're really talking about you project polytopes, you ask about where's this phase transition, and so on and so forth. There's some related ways to think about compressed sensing where you have slightly different rules of the game, and so you can calculate in a different language, maybe using the tools of another branch of applied mathematics, and you see that that same form of result coming up. Jared, can you help me with that? Who has come up with? Isn't there information theory versions of that?
Martin Wainwright at Berkeley.
Yeah, so in Martin's though, it's the ratio inside the 2 log n is at a different place, right? That's instead of k over n, it's like I was thinking, didn't Rich Baraniuk do some calculations? I think Rich Baraniuk at Rice may have done some things using calculations from the broadcast multiple access channel. So it turns out that, you know, wireless communications has a lot of stuff related to this, and they have their own way of looking at it if you've been working that field. So what it seems to say is if you have, if there's k things that you haven't measured appropriately because you don't know where to look, and they may be located anywhere among capital N, right, then there's this extra log factor. And we're used to things like that in information theory. So post facto, it looks quite reasonable that it's there. And the interpretation could be that it's the number of bits required to specify the location of those particular entities. Am I getting to the point you wanted to make?
That's right. Yeah, I think I've heard it put forward that may be where it comes from. Interested in your views on it.
I wanted to show one picture, if I might. John Wishart was the head of the statistics laboratory at Cambridge. And in the middle 1930s, he worked on random matrices and came up with the exact formulas for what's now called the Wishart distribution. And there's been amazing progress in the asymptotic analysis of everything to do with this distribution over the last 10 years. I dare say there must have been, in fact, whole long programs here devoted to that, but I can't cite you the specific. I know that this, random matrices are very heavily studied, but statisticians have had a lot to do with random matrices over the years, and you start to see applications of them that are quite non-conventional. So as a statistician, just wanted to honor a true Cambridge type who saw the importance of random matrices many decades before anyone else was thinking of them.
Good. Any other questions to David? Yeah, please.
So, your talk viewed from my perspective, which is, I guess, what everybody does, as a Bayesian statistician, I guess the argument that I see is for using sensible priors when solving difficult inverse problems. And sparsity is a lovely prior. It's a principle that appears in lots of different priors in the real world. What I'm a little more skeptical about is the random matrices, since we have a picture of Wishart up here. Now, if you were to design a sensing matrix for smaller p and n, then surely you can do much better than random matrices. Or
okay, so there's a couple of things there that you're bringing up, and I'm quite remiss as a statistician, by the way, in not bringing in the Bayesian story. So I did give a talk in January where I spoke a lot about deriving the Bayes risk in these situations under a particular kind of prior. And it's, I think would be quite interesting to statisticians or people who study spin glass theory. I just felt for a general audience it might be so narrow, but definitely I think like you, and I'm just trying to give a talk for another audience. The second thing that you brought up about that you ought to be able to do better than random matrices. Jared and I have tried that. A lot of people are trying to come up with deterministic matrices. But the kind of phase transitions that the curve that we showed and so on, we found that matrix ensemble after matrix ensemble is just kind of right on there. There are matrices that sound like they ought to be great, and it's just really hard to see that they beat it. Yeah, they're just right on the line. They just do the same thing, but they seem much more persuasive than random matrices.
Any other questions or comments? I mean, if I may, just one quickly from me. I mean, another example which I was exposed to, which may come into this category, is actually X-ray crystallography. I guess it's a little bit like MRI, where people have basically used what seemed to be in the past magic to attempt to determine crystal structure from result. Right. Is that the kind of area that you've looked at in terms of the sort of sensing compression, or does that?
I'm aware of the problem. There's some, it would be great if it could be used. There's a nonlinearity there that stands as an obstacle, which is instead of observing y, in some sense, we observe the absolute value of y.
Right. Yeah.
And that makes that completely changes the character of the problem. But I should mention something which is another distinguished English professor of days gone by was Dennis Gabor, who was at Imperial College and won the Nobel Prize for holography. And I was reading through something that he said, and so in the late 40s, just after he finished doing war work for, I guess, RAF or someone like this, he came up with the idea that you should take a really lousy picture, but that it would have all the information you need in it to reconstruct. That what everybody else was working on was trying to take really high quality pictures. He wanted to take something that he wanted to take data about something where the data contained the information, but you couldn't physically see the original image in those data. And that was a very far-sighted thing, because that's exactly what's happening here. The measurements that one would take with a random matrix don't anywhere in themselves betray what's going on. It's only after you do very sophisticated reconstruction that you get somewhere.
Great. Well, everyone is invited to the reception outside, and I do hope you'll join us there. Could we all thank David, please? I think it's been a fascinating talk. I mean, for me, it's the beautiful maths of these high-dimensional polytopes. What's that got to do with anything? And the answer is a fantastic range of applications, and this is maths at its very best. David, thank you very, very much.